two springs. We got some sort of weird graph over here. Force distance. That's interesting. Hopefully by the end of this, you'll when I say force distance graph, you're like, oh gosh, that means, but not yet. I think this is 0.3 and 30. Does anybody disagree with me?
No.
And then it ends at what? 0.570?
Yeah. Oh.
I'm just trying to do what the graph looks like. Am I right?
Yeah.
All right. Not trying to do anything fancy other than draw what it says. Then we got a block that's sliding along, 1 kilogram. Slams into these. No, I'm sorry. It's pushed against those things and then let go and figure out what the speed is, and it leaves the springs. Clearly, it's an entry before it's an entry after problem, correct? Balzac? You'll allow me that? And what kind of energy do I have before?
I'd say
potential energy. Now, potential energy of springs, that's different, though, right?
yes.
Well, it's new. It's not MGH.
Right. Why does potential? Because if you're like loading the spring.
I'm totally with you. It's actually potential energy of spring. It's a little early for us to discuss it that way, and I'm going to make you change it to something else in just a second. But that's the right answer. That's actually exactly what you should say. Potential energy of the spring. Of course, now you should be panicking. How do I know what potential energy of the spring is? Right? That's something brand new we've never dealt with. Over here, what kind of energy do you have?
We have kinetic energy.
All right.
Let go.
Anything else?
I think that's it.
Okay. There would be some heat and sound, but we ignore those as always, so we're going to keep ignoring that. All right, so moving forward, potentially the spring. I don't know the potential energy formula of a spring. One of the things you can do, though, to find a potential energy of anything is how we did it initially, which is we figured out how much work it takes to do the same thing. I mean, we did work shoving that block in. Agreed?
Yeah.
That work will equal the potential you have once I get ready to let go of it, correct?
Yeah.
So instead of doing it as potentially in a spring, which I'm not really sure what the formula would be for that, I'm going to say work done getting it into place.
So it should be work.
So that'd be work.
Equals. Okay.
All right, give me some formulas.
So we got negative, so 1/2 mv squared, and then force
In the same direction, which in this case it would be the same direction. Okay.
So how do we account for two springs that are different?
That's what we're going to talk about. That's why this is a problem, not an easy. Like that's it. And the fact that springs, everything about this problem is a nightmare. Give me a second. We can figure out this side 1/2 1v squared, right? So that's really not going to bother us much. So for force times distance, what am I going to do?
Well, let's see. I don't know quite how to do distance once.
Well, how far do they push it in?
0.5 meters.
0.5 meters, okay.
So that'd be distance.
I don't know. Would that be the distance?
Yeah.
Let's try it out. This is a thinking man's game. We're going to have some trouble here. What force am I going to use? I labeled that as 70 at the top. So that's what you're looking for.
All right, so 70.
70. So now I'm going to disagree with you. Why am I going to disagree with you? Well, because did this person apply 70 newtons the whole entire time? When they first started pushing back the spring, did they provide 70 newtons?
No, that's just when it's at.
At the very end, he has to hold it there at 70 newtons, but up to there, he's not even providing 70 until the very end, right?
Yeah.
So did he do that much work? 70 times 0.5?
No.
No, he did less than that, didn't he?
Yes.
Now what are you going to do? That's fair. That's exactly fair. In fact, I'm asking you to do a calculus problem. Totally fair. But this is a algebra-based class, and so we're allowed to access it if it looks like this. The reason why it's a calculus problem is because the force is always changing the whole entire time.
Because he's doing different.
Right, but he's going to be pulling with different forces, so you can't say what force he pulls with. And you can't do force times distance if it's always changing, right? You have to do like every millimeter, or every quarter of a millimeter, every tenth of a millimeter. You couldn't do it. But we've done problems just like this before. And in fact, it's probably the only graphing problem we've done this year. I'm probably wrong. You ever do any graphing problems, sir?
We did like the unit one.
Yeah, what unit one was?
When you like the acceleration time graph.
Acceleration time graph. Okay, let's do acceleration time graph. The acceleration time graph, and the area of the curve is what?
How far it's going.
No.
How fast it's going.
Yes, it's velocity. Because as you know, v equals v naught plus at if you assume a zero initial velocity, which we'll assume for this purposes, then at is equal to my velocity. And so the area is my velocity. We made that reasoning. We worked all the way through that, didn't we?
Yes.
Then we drew VT graphs. And the area of that was what?
The distance.
That's the distance. Because we know distance equals velocity times time. So the area told us the distance. And so there's a much more profound thing in what we did in chapter 1 than simply solving for velocity or displacement. Actually, the area underneath the curve is equal to this times this, isn't it?
Yeah.
Which, when you normally have a constant velocity, is boring, right? Because velocity times time would just be a rectangle and length times height, right? You'd just VT. But when it's changing, it still works. When he's first pulling on the spring, he's hardly using any force at all. He's doing basically zero work. As it goes up, it increases work. So does the area of the curve.
Okay.
And
So 5 force we have to go.
So to get how much work it is from here to here, we're going to have to do the area underneath the curve from 0 to 0.5.
Oh.
Combs? This is huge because on the AP test, I'm going to want you, when you see a graph that looks like this, I want you to say, force distance graph, the area is going to be the amount of work I'm doing. I want you to think about that before you even read the question going forward. Any two things multiplied together this whole entire class. If there's a graph like this, area of the curves are two multiplied together. Right? Oh, look at your faces like I made something up. All right, so I just did a triangle, and a rectangle, right? And so I get the amount of work I did is going to be 4. That's just 4. So you calculate for that. That's 9. It's 4.5, right? And this would be 6.
Wait, what was your final answer for the area?
I'm doing it right now. I got 14.5.
What?
I got 14.5. Two people said what?
60.
That's a bad sign.
I got 13. Are we using 30? I got 14.5.
We said, I said this is gonna be 30 at 0.3.
Wait. Isn't it 70 at 0.5?
It's 70 at 0.5. Did I do that wrong?
So isn't that 0.4?
Right. Thank you. Is that point? So no, 0.2 is the bottom. It's 40 up.
Yeah, so 40 times 0.2 over 2.
Well, 1/2 of 2, 0.2 is 0.1. 0.1 times 40 is 4.
Yeah. And then the other one's 30, right?
So it'd be 1/2 30. Oh, that's where I got it wrong. This is 1/2 40, wouldn't it?
Oh,
What did I do? Oh, that's this section. No, I'm wrong. 1/2 30 times 0.3. That's fine.
yeah, that's fine.
And then this one's going to be 30 by 0.2 rectangle.
Yes. So
I got 14.5.
there. Wait.
I'm getting 14.5.
That sounds about right. That's just 14.5 equals 1/2.
B squared and solve. You're home.
That was not as gnarly as I thought it would be.
A huge concept, though.
I did 4 plus 4.5 plus 6. Wait, where did you put the 4? So the 4.5 is 32.69. That's
Good? All right, I'm going to pause this for
Negative a times x.
negative k times x. I'm just going to use kx, but you know, the negative is just a direction thing. So far, so good?
Yeah.
Yes? Winter, you good?
Yeah. Yeah.
Okay, now I want to multiply this times distance, because I want to do a work, so I can figure out how much energy I'm storing in my spring, right? Because I have spring. I'm going to squish it in, right? So I'm ready to launch it.
Yeah.
The work would be force times distance. And I do work equals kx times x. And unfortunately, I'd be wrong if I did it that way. The reason why is this.
what problem is this, Reggie?
It's a brand new pro. You're going to have to write down some notes someplace random because I don't even have a spot for it on your notes. It's terrible. I don't know I don't know why spring is disappeared. I deleted it somehow, some way. So, when I first start to push in this winter, how much force do I apply on that spring?
Wait, for what question?
I'm about to push. I'm very beginning to start to push on a spring. How much force would I apply?
Well, doesn't it depend how hard you're pushing it?
No, it does not.
0?
0. So it's going to start down here, isn't it?
Yeah.
Now, x is my x-axis, which is convenient. F is my force. So if I was going to graph this equation, isn't that a line?
Yeah.
Whoop. So far, so good? And so that's what my force versus x would look like, correct?
Mhm.
Now, if that's the case, how much work am I actually doing? Because this formula won't work for me because you said there's 0 at the beginning.
Yeah.
So let's say I move at a distance x. How would I figure out how much energy a spring would have?
When you just find the area,
Which would be?
f over x divided by 2. Or like f to, yeah.
F times x, wouldn't it?
Yeah.
And by the way, I'm going to change that f to kx times x. And then I'm going to do one more rotation to it. I'm going to say what? Oh, that's not equals 2. That's what I don't want. Hold on. Equals 1/2 kx squared. This is the energy of a normal everyday spring. New formula. Write it somewhere in the first 2 pages and circle it like 8 times and then highlight it twice. What color should I use, Mr. Sussman?
Whatever color you want.